And finally, for postulate 5, we have that the wave function evolves in time according to the time-dependent Schrodinger equation. And this time-dependent Schrodinger equation, sometimes abbreviated as the TDSE, is h psi of xt, so the Hamiltonian acting on psi, which is a function of both position and time, whatever position variables there happen to be, in this case just one dimension x, equals I times h bar square root of minus 1 times the reduced Planck's constant times the partial derivative of the wave function with respect to time. So before we were looking at the time-independent Schrodinger equation, and this is what the Schrodinger equation looks like when you include time in the mix. So this is the final full guts and glory version of the Schrodinger equation that we can use in quantum mechanics. So we're going to look at this a little bit to try to derive a nice general relation that we'll see later on. So let's assume, as we have for many cases, that our wave function of space and time can be separated into a function which depends only on spatial coordinates, and which we'll call little psi, this being a capital psi with the sideways bars. I'll try to remember to put that sideways bar on there when it's talking about the time-dependent wave function. So some function of space times some function of time, let's just call it phi of t. You can call it whatever we want, we're just going to call it phi of t. So if we substitute this in up for the time-dependent Schrodinger equation up there, we're going to have h acting on psi of x phi of t, close the big parentheses, I h bar partial derivative of psi of x phi of t divided, and then that partial with respect to time. But usually our Hamiltonian is not going to vary in time. Our Hamiltonian is going to have an operator which is kinetic energy, which are spatial derivatives, second derivatives with respect to spatial coordinates, and a potential energy function which varies in space but generally does not vary in time except for very few cases. So we're going to assume that the Hamiltonian is constant in time. Therefore, we can pull out the phi of t here out in front of the Hamiltonian and just have the Hamiltonian act on psi of x. Similarly, the spatial part of the wave function does not depend on time, so we can pull that out of the derivative with respect to time and have I h bar psi of x. And because now the derivative is only acting on a function whose only variable is time, it becomes an ordinary derivative. We just have d phi of t with respect to t, ordinary derivatives. Then if we divide both sides by phi of t psi of x, we will get to this equation here, h psi over psi of x equals I h bar over phi of t d phi of t dt. So just as we saw with the classical wave equation, we've got a function here which varies in space, a function here which varies in time. The only way which these two can be equal to each other for all values of spatial position and time is if they both equal the same constant. And we're going to call this constant E, and that's by design because this is going to end up being the energy of the particle with this wave function. So then if we take just the h psi over psi equals E, what we end up with is h psi equals E psi. Just taking this first and last part and multiplying by psi, we get our familiar time-independent Schrodinger equation, and that was which we just get from a separation of variables of the time-dependent Schrodinger equation. An assumption there and an assumption that our Hamiltonian does not depend on time gives us the familiar time-independent Schrodinger equation. So that's good. but we also want to figure out what the heck this time function looks like. So let's continue on with that. We're going to have, taking this function here, we have d5t dt, and this times 1 over 5t equals, then dividing e by I h bar, it will be the same as, that'll be the same as e over I h bar, but because of the properties of how the number I works, that's the same as putting a minus I on top. And you can convince yourself of that by seeing how I squared equals -1 and working that out with the whole numerator, denominator there. But it's going to work out. And then next step after that, we have this dt here. Let's just multiply times the dt on both sides. We end up with d phi of t over phi of t equals minus IE over h bar dt. Then a standard trick in ordinary differential equations. We've separated now this ordinary differential into both sides, and we're going to integrate both sides. So this side integrates with respect to phi of t, this side integrates with respect to time, and what we get is the integral of 1 over x, or 1 over phi of t, is the natural log. Let me get a new color. You get the natural log of phi of t from that integral equals, and over here integrating dt gives us just t, gives us minus I e t over h bar. And there would be some constant on this side, but that constant is arbitrary, and we can pick it to be anything, and we'll see that in the end it just would affect the normalization constant anyway. So we're going to ignore that constant and just not worry about it, and then continue on. But then taking e to the both sides, we're going to end up with our final result, which is that phi of t, the time part of the Schrodinger equation, equals e to the minus I e t over h bar. So that's our time piece. That's very nice. That's just a nice little function. It's a complex exponential because we have an I in here, so it's going to oscillate back and forth in time. It's going to oscillate faster as the energy gets higher, and then we have this length scale here, which is dictated by h bar. So this is going to be important at very, very small length scales. So putting that all back together, we're going to get our final result, that going back to the psi of x and t, multiplying the two back together, that we get the spatial part of the wave function, which we solve from the time-independent Schrodinger equation, given some Hamiltonian, given some potential energy function, times e to the minus I e t over h bar. And in a couple videos later, we'll see what practical significance this has and how this time piece can really affect the properties of a system depending on what the wave function of that system is.